So this week, we want to talk quickly about, we're going to talk about machines. And then it sounds like Vincent will be here once he's got dinner. And we might do some more working on things here. Setting up the 3D prints feels like an easy goal for today, to take the designs that we can download from online and print some of them, maybe especially those that we don't have to modify very much. We can make that part work. But today we're going to focus on the next piece of what you're doing when you're building a machine. Some of this is going to look back a little bit on what we had done, but some it's mostly going to look forward. And so again, I like to think about building a machine with these different parts, the active components, the physical structure, and the code base. And so we're just going to be thinking about sort of each one of those pieces as we move through the project. And mostly this time, last time we talked about physical structure quite a bit. This is going to be a little bit more on the active components. So we're going to focus on the top of that triangle. So machines 19.2, I need to update the number there. But we're going to focus on movement and end effector and how you'd do some of that work, which is also really fun in that you can have an end effector without motion. And that's what Vincent and I were working on yesterday, trying to get the back door to work. We were really just working on the low level control to make that happen, and then trying to figure out how to do higher level stuff. So this week, we're just going to try and focus on the active pieces of the machine, the things that are like making it move, heating it up, doing the cutting, all of those pieces that are very proactive in what they do. So the main part of this is going to be just sort of wrapping our heads around what those pieces are, what they're called, and how you might do some controlling with them. So to try and make sense of that as an overall, motion is a critical element of almost any machine. Exceptions are like the ones that Vincent and I were working on, where it's just trying to open a door. If you've got something that's just sort of an electronics project, it may or may not need to move at all. But for most of the CNC machines that we're going to be working with, motion is a big part. So there's some different categories of movement, different ways that you can make things move. We're going to try and break these down as much as we can to try and understand them a little bit better. But essentially, I would put motion into these two camps. There's linear motion, where you've got like a stepper control. You can have dual or parallel motion. There's actuators when you want to have like a short little ding, ding, ding. We saw the xylophone that was a bunch of solenoids. That was a actuator short motion. Then there's different drive mechanisms. So you could have a lead screw to drive things, a rack and pinion, a belt drive, a chain and sprocket. Those are all different ways that you can communicate that linear motion that are a little bit separate from what causes it. So there's the thing that causes it, usually a stepper, and then there's the actual way that you communicate that. The thing that is currently my picture on screen, and we'll look at this a bit more, but these are all belt drives. So this right here is a belt, and the belt drive would be attached to some sort of a thing that slides along. So you can see here there's a little linear bearing right in there. And this would be drawn along the structure of the machine sort of this way by the linear motion from the belt. So a motor turns, a motor like this one turns, nope, just in view. And as this motor spins and turns, it's able to slide this piece along its length. So ultimately, that's our belt drive. We're going to try and better understand it than this mess right here by looking at a few clean examples. So there's that, and then there's rotary motion. There's a couple of ways that you can do rotary motion. You can do high speed rotation. You can do high torque, where it's geared and you've got lots of torque behind it, just a stepper. And then there's also actuators, and I'd count servo motors in that camp. So there's a few different things to take into account when we're looking at all of these. But basically, I want to think about these different versions. So I like this graphic, and this is taken from Naughty Peak's Machines That Make website. It's the gift that keeps on giving. But these green stages are those cardboard stages that can move along each other. So you can imagine sliding along this way or sliding along that way. And so you sort of have two-dimensional motion. Or here you have linear motion along this one or along that one or up and down along here. This is got the ability to do some sort of linear motion also. Here's a rotary axis. So you might have a rotary axis that is attached to things. Here's two rotary axes along a slider. This could be really cool if you're doing like camera work, to have one of these in a camera mounted, where you can rotate it in 2 dimensions and do a linear slider. There's all sorts of different connections that you could make, and these are all just sort of representative diagrams of what those might look like. But we're going to try and understand a little bit better about what it is to try and make that happen. The most common of these, one of the most common, is a lead screw, just like this, and they're really helpful for making things happen. The Gerber actually uses lead screws on all 3 axes, which is interesting. The biggest tool that we have in a CNC machine to make things move reliably is the stepper motor. And so yes, last week, if you were here and we started tearing apart things, you saw these weird square or rectangular motors. Those are stepper motors. Internal to a stepper motor is different than like the normal DC motor. If you just apply a battery to these motors, nothing will happen, or it will magnetize, but nothing moves in a big circle. You might get one step and that's it. These motors are special motors that are designed to work in a certain way. Each time you apply power, you get 1/200th of a rotation for a lot of them. And so that's not very useful. What you need is a driver that pairs along with it so that you can get this crazy circuit rotation down here. So the 4 different coils that are inside the motor can be activated in sequence, and you can make it spin. So when you do this, you have the ability to drive this shaft an amount around, but because each time you activate a step, it's 1/200th of a rotation, you can very accurately say, I'd like you to make 1 complete rotation, please. And then it will activate the right number of steps to make that happen. That's the magic secret of all of these machines, is that you have motors where you can say, I'd like you to move forward 200 steps. And maybe that's like conceptually obvious from the beginning, but this is really the key move. These fall into the category of brushless DC motors. So they're direct current motors that are brushless, BLDC motors, brushless DC motors, and they really do a great job of this one thing. But really they're hard to control without a dedicated chip. So this is a common chip that you'd use, a quadruple half H driver. And so this is an H drive circuit. You need this sort of control to drive one of these. And it means that this was not a thing that would have existed prior to a digital controller for a motor. We really couldn't run these. There's no way that Michael Faraday could have invented one of these. Not because it's electrically that complicated of a motor, it's fairly simple, but because you needed the electronics to control it so that it could happen at very high speed, so that you could get it to move through those steps. Another nice benefit of a brushless motor means that there's no like possibility for spark. Many of you have used a drill and seen it spark out of the back, or maybe even smelled the ozone that comes from the brushes. Brushes are a great way to get a motor to work easily, but they introduce a chance to reduce a little bit of torque. They have their own problems. And it's what happens when you have the coils of wire inside of a motor. There's always a permanent magnet and a coil magnet. The brushes are needed if the coil is on the spinny part, because you can't just wire it in, because it won't be able to spin for forever. It can only spin until the wires get snug. So a brushless motor solves this problem by putting all the coils on the outside of the motor body, and then the inside piece, what rotates, is the permanent magnet. And so that arrangement is really cool, but it means that your motor drivers need to be more complicated. So this is, in any case, this is the common way to do this. All of the motors that are depicted here are stepper motors. This is one that might be in like your inkjet printer, the printer that you got for free with your computer. This is one of those. They're very small, they're very cheap, and they work fine for what they're doing. To move around a little inkhead and just print, this is totally what's working inside of there. These bigger ones are going to be for 3D printers, or these really big ones, sometimes they get called robot servos if they have controller stuff on the back. But these are all different steppers that are in play. This is the central motor that makes any CNC machine work. So if you want to know how the Gerber works, you poke your head underneath the table and you'll see one of these stepper motors. They're there on the laser cutter. There's those hidden away. If you were to tear open the housing on the vinyl cutter, you'd find them in there as well. So there's lots of places where these exist, but oftentimes they get understated. Even your standard inkjet printer at home has stepper motors inside so that it can move the print head to right where it needs to lay ink down to dot your I's and cross your T's. But from there, your steppers can have lots of different endpoints. The ones that we saw here just have little shafts that come right out the top. But a common one that you might have is a long one like this. So instead of a short shaft, this has a lead screw in its central axis. And that means that it's ready to go as the Z axis of things like the Prusa. So the Prusa and an Ultimaker, these are both different types of 3D printers. They use a stepper motor with a lead screw right attached as the shaft. So there's no gearing, there's no nothing, there's no belts, none of that to deal with. The lead screw comes right out of the motor. And the Prusa does this successfully with two little steppers. So the steppers down here you can see are fairly short, which means they don't have much torque in either of them. So it uses two in concert to raise and lower the 3D printer bed. It's really nice. It's a very elegant way to get the stepper to move up and down, or to get the print head to move up and down on a Prusa, but it has its own like costs and benefits. You don't need to buy as big or as beefy of a stepper motor, but if those two get out of alignment and the whole like X-axis array gets tilted at an angle, you've got a bit of a problem. So there's some interesting things. It's a nice way to balance weight and load, but this is something that's tricky to keep working consistently, and Prusa has really figured out the trick. Over here, the Ultimaker is another type of printer, and this one is different than the Prusa. The Prusa leaves its bed mostly on the bottom and doesn't move it much. The Ultimaker just takes the print bed and it moves it down, 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 down through the entire print. So it's much more like our Markforged printer in that it starts the bed off high and then it lowers it as the print finishes. In this case, you also can see a lead screw here in the back, but it has these beefy rails so that the lead screw is just raising and lowering, and it's not really fighting against the tilt of the bed. The bed would want to sort of flop forward if it was let to go loose. And so these are two different stepper motors that you might use for a Z stepper. And Z steppers are a common way to get the printer or the print head or the print bed on a 3D printer to move up and down. They're great, but they don't have very fine control because one rotation happens with 200 steps. And that sets a limit for how finely tuned you can be. There's no gearing in there, so it's not as easy to make it very fine tuned. The like practical consequence is that if you're 3D printing something and you talk to the 3D printing facilitators, they're just going to flatly tell you, oh, the Z-axis has always got the worst resolution because the belt-driven gears have better resolution, and the Z lead screws, they just can't get as many steps into 1 inch of motion, or a few millimeters of motion. It's an interesting consequence of the way that they're built. However, stepper motors work great, but sometimes you don't need all of the control of a stepper motor. Good examples are in servos that you might use for RC airplanes. So if you just need an actuator movement, that's like a short swing, maybe not with a lot of torque, or maybe with a fair amount of torque, but an actuator is something that's just sort of a short swing of a motion. And so this is a good example to think about here, where you've got a little tiny hobby servo mounted, and then your pen on a plotter has just got to move up and down, not very far, and it's not a lot of weight. It just needs to move enough that it's writing on the paper or not writing on the paper. And so in that case, you don't need a full stepper motor. You can use a little actuator that'll just act and unact. And servos are a really good way to make actuators. They've been used in hobby RC planes for a long time because they're very lightweight. They behave very predictably. And basically the standard communication protocol for a servo is set by RC hobbyists. They've been using them for so long that they have set the electronic standard for how a servo works, which is really fun. Servos can do this job really well. The very small light ones are pretty wimpy, but you can get very, very beefy servos. So it's possible to really upgrade all of this. It's also fun to see on an airplane where all of these actuators would go and live. And on a real plane, they're also called actuators. They're just linear actuators, and they're a whole category of motor and motion unto themselves. But it's neat. If you want to spin something at high speed, there's essentially two ways to do it. You can use a brushless DC motor again, like a drone motor, or this is a hard drive motor. So these are different types of motors here where you have the spinny bit is the permanent magnet, and then you can see the several wires coming off here. On the windings, those windings stay in place, and in the middle would be where a magnet lives that spins. So the permanent magnet is the spin part, so you don't need to put electricity to it. You're just applying electricity to the coils on the outside. Same is true for a drone motor. It lets you, brushless motors can spin faster because of this. In general, you can make them happen a lot faster, but they're more complicated to drive. These are the simple brushed motors. These have been a staple of how motors work for a long, long time. Now, I call these brush motors, and it's hard to see, but this right over here is the brush itself. So those two little strips of metal, those go in and they touch this thing here called the commutator ring. And you can sort of see right here, this like cyan and the yellow. Those are the two brushes. And then this orange thing that's rotating, that's the commutator ring, and it's a split commutator. That's the actual mechanism. If you ever really feel like nerding out, those like $1, $2 fans that you buy on a hot day in a theme park that just you hold, they run on 2 batteries and you blow yourself in the face with a tiny sad fan. Those things are really fun to take apart. The motors look just like this. They must cost 50 cents to make. And they come apart fairly easily. So you can actually unwind, or you can take them apart, disassemble. You can see the permanent magnets in here. You can see the coiled magnets in here, the commutator and the brushes. And all of these are laid out really nice and cleanly. There's plenty of things to look at with these. Like there's lots and lots to consider. You can go way down the rabbit hole in trying to understand motors, but it's fun to know that there are these different categories. Brushed or brushless motors, you might need high speed. In general, for us, if we were making a CNC that needed high speed, I would only expect it to be for the spindle in order to spin the end mill, like on the Shipoko or the Gerber. So probably not a thing that we're going to need to know much about. But this is, when you're doing this, really, ultimately, this motor, you're not going to be able to finely tune control like a stepper, but you can control how fast it spins with a fair amount of precision. So you could say, I want 16,000 RPMs is something that you could control, but it would be much harder to say, I'd like you to make 1/4 of a rotation, because the commutator just doesn't let you get that precise. So those are all interesting features. Then you can gear things for high torque, which is another fun process. If you have a motor and you find that it's just not beefy enough, you can add a gearbox to the front of it. And so there's all sorts of these gearboxes that you might add in. I'm playing this little video down here where they go through gearing a whole bunch of Lego pieces. But here's a DC brush motor with a gearbox on the front. You might have seen that when I was a kid, I would find these types of motors rattling around in a garage much more often. And I'm not sure why, other than it's hard to find and replace these geared motors. This is a gearbox on the top of a stepper motor with some sort of a feedback loop back here. These sorts of gearings can really help. Here's a worm gear drive. This is a nice way to not only change your direction 90 degrees, but each one rotation of these advances this big outer gear by just 1 tooth. So the gearing is really aggressive on those. These are often used on something like the Bridgeport. Then there's these like hobby DC brush geared motors where you've got a whole bunch of gears going on with this motor. And so you can get a big time reduction. This is still going. Eventually, if you watch this video, they get to a point where the gearing is just so high that they can actually, you can not see it spin, that it might take a century for a full rotation of a gear, which is kind of wild that you can build something like that with Legos. And so they're just going to keep going. And really, ultimately, gears like this are important for understanding how motors work, because a motor basically always has to spin quickly in order for it to work. It's just a feature of how it operates. It must spin fast. And so in order for a Tesla to be able to spin the wheels at 1 mile per hour, it's going to need to have some sort of a gearbox that will take the high spinning motor and gear it down so that the motors can operate with enough torque and that they can operate at the speed that you want them to. So all of that is going to happen through a set of gearboxes. And I think that, as electric cars get more and more popular, we're going to have to think a lot more about these gearboxes that are tied to motors. Instead of transmission gears going out, maybe we'll have motor gearboxes going out on those cars. But that is yet to be seen, I suppose. All right. So you have all these different types of motors, lots of things to think about there, but how do you get those to actually move something? And here's the 4 main strategies that I would encourage us to explore. And we're mostly going to just be thinking about belts on the machine that we've decided, but that's by no means the only way that you can get things to move. We saw that a lead screw works perfectly fine. The Prusa uses this extensively for its Z-axis. And these are relatively cheap to implement because it's all one part. And so cheaper and cheaper printers will use these more and more. But a lead screw, the nut here doesn't spin, but the shaft spins. So because the shaft spins, this little brass nut will slide up and down along the lead screw. And it's a really fun thing to play with. If you have those parts loose and separate, you can watch the motor sort of spin and fall down, and it'll move through. You might have even, I don't know what your teenage self did when you were bored, but spinning a nut on a screw on a long bolt is kind of fun. If you're growing up in the Midwest in Ohio on a farm. So, but playing around with that, you can imagine sort of how if you spin the screw underneath the nut, it moves along some distance, or if you spin the nut, it advances on the screw. And so it's just taking that idea and really taking advantage of it for a lead screw. Even though there's motors where these are directly connected in, you can couple them on with a shaft coupler. This is pretty common for a stepper that doesn't have a lead screw, and then you want to attach your own separate lead screw after the fact. So a coupler like this works. The spiral cut is so that if they're not perfectly aligned, it'll sort of bend into place. My favorite and probably the nicest way to make this work is a rack and pinion gear, like a full proper rack and pinion gear. It takes a lot to get this system to work, and it's probably the most expensive of the pieces. But if you do it right, you can have really good engagement, really efficient transfer of energy. And so you can have some really cool motion things happening here. The Gerber does not use this. The Gerber uses just lead screws. But the ShopBot, which is another type of machine, sort of in the same family as the Gerber, uses rack and pinion gears. And I would be shocked if the Tormach didn't use some of these also, because they're just a good, strong way to transfer power back and forth. They do pretty much serve as a huge pinch risk. If you ever got your finger in there, you'd have a big problem. But in general, these are really, really nice ways to transfer motion from a rotary piece like this gear here to the rack that's moving along back and forth. It improves torque a lot, but it's really an expensive game. Chain sprockets are a fun way to think about it. This is, you might on a motorcycle or on a chainsaw or any sort of tool like that or machine like that, you might use a chain to transfer energy, even a bicycle. And so chains can transmit energy and motion, which is really an important feature of how they operate. And they don't stretch very much. They don't squish almost at all. And so you've got this really steady length that is able to flex and bend, but it doesn't have any give or stretch to it. So that is a really cool mechanism that's been used also. And people have designed entire CNC machines. This is the Maslow CNC. You can see it's got basically a palm router that is held onto a thing with a couple of bricks mounted, so it's heavy. And then it's got 2 chains coming off the left and right. Then it uses polar math, like a weird math variation of coordinates, to be able to CNC just like the Gerber does. This was advertised for a while as the CNC you can hang up on the ceiling in your garage and then drop it down whenever you want to use it. Because ultimately, it doesn't really take up that much space, and the chains work really well to give you nice control. This actually works beautifully, but a problem with it is that it uses sine and cosine, those functions, which are sort of error prone over on the right and left extremes. But if you're machining in the middle of a sheet of plywood, works great. So this is a fun mechanism that you can use. and this is one that we're not going to explore, but it's a really cool one to try and better understand how these fit together. And then the last bit is timing belts. Timing belts are a tried and true method to communicate motion. If you ever have owned a Honda, you know that they have a timing belt in the engine that will need replaced at 90,000 miles. And a tooth belt like this works really well in lots of different applications. So the timing belt in a Honda or the timing belt in a 3D printer, they all work the same. They've got these teeth, they go along these gears. And as long as all of these mesh and are the same tooth density, the same size, this can be a really nice way to get motion to bend around in lots of different directions. You can use a couple of gears like this. Sometimes they have edges on them to keep the belt from sliding. Sometimes they don't. You can use an idler pulley like this, where it sort of presses it in from the side and holds it all together. All of those are good tricks with mechanisms like this. So you can have a good connection with a timing belt. You can also sort of just clamp it down on the edges. And that's what's happening in, let's see, I'm gonna make a quick transition. That's what's happening in the examples that I have over here. Let me do a stop share and show you what's going on. So here's the timing belt that was used to move this piece back and forth. And you can see it's somebody just literally put bolts through it, and that's it. It's held down with washers and some bolts. There'd be holes in it right there. And that works like a charm. Here's another application where they just wrapped it around, zip tied it to itself, and then it's wrapped around a couple of bolts, and that works just fine. And here's another one where you can see it's a continuous belt, or maybe you can, I don't know what my framing looks like, but it's one continuous belt. There's no breaks, there's no end, it's just a big loop. And they only clipped it onto here by sort of threading it under this moving carriage. So there's lots of different ways you can play with timing belts and use them. And here I've got an idler pulley on this side and my little drive gear over here. Those are all different ways you can play around with these timing belts, which is a really useful way to get motion to happen inside of a machine. So let's say you have a motor selected, you have some sort of motion system selected. The next thing that your CNC machine is going to need is a way to know how many steps it takes to move a millimeter, or steps per inch. This is something that is really essential to how the machine operates. When you send G-code to the machine, you're not asking it to move steps. The G-code should actually be ignorant to how many steps there are in the machine's motion. You're just asking it, please move forward 6 inches and over to the right 4 more inches. You're not trying to ask it how to do the actual steps pieces. You're just trying to get it to go a certain length.
For like a second.
Yeah, hold on. We're gonna pause for a second of video. What's up?
So I keep making something because the girlfriend's hamsters passed.
Oh, I'm sorry. Yeah. Okay. Do what you gotta do. Have a good night, as much as you can. Yeah. See ya. All right. We're back in the editing game. It's 7:37. Okay. So steps per millimeter. So basically, when you input your controls for this, a CNC machine is going to take in the direction and dimension that you want it to go, and then translate that into steps the motor spins. It keeps your G-code a lot simpler if it doesn't need to know how many steps, and that's all managed in the firmware of the machine. And so basically, there's calculators that you can use to do this. For a lot of machines, the Shipoko before this one, you had to tell it what size of linear of lead screw it was using, so that it would know the right way to have steps per millimeter. And without getting this right embedded in the machine's firmware, the machine will try and move, but not move as far as you want, or move too far. On the Shipoko before this one, I had it cut a piece, and it cut everything that I wanted, but all of the features were shallower than I was hoping for, because it had the wrong calibration for steps per millimeter. So it thought that it had moved down 1 inch, but it really only moved down about 1/2 inch. So everything was just sort of squashed to be shorter than it was supposed to be. It was a very perplexing issue to solve after a while. But we did eventually get it. One thing that you can do to try and improve your machines, and this was common in early 3D printers, is people would use stepper motor micro stepping, where they take each one of those 200 steps and they can divide that by 16 again. So you have much more resolution. But when you do that, you have to change your steps per inch to be 16 times as many steps per inch. So it's an interesting dynamic to get that all to work. But it's stored inside the machine firmware. You shouldn't have to deal with it. The nice thing is that we will, fingers crossed, only need to do this once in order to get it right, and our machine will be happy for forever on. But basically, if you've got some sort of a machine, the magic of the machine always happens at the end effector. So the end effector is where it does what it's going to do. And so for most 3D printers, that's a hot end nozzle like this, where you push in plastic in tube form or in a stringy form from the top. It passes through this chamber where it's still not quite hot, and then it gets down to this very, very bottom. And in that moment, it melts it and oozes it out the bottom. And that works great. Coming down off of here, there's two wires coming out. There's the red one, which is power to the hot end. And then this one is the thermometer that actually keeps track of it to make sure that it's not too hot, not too cold, right on target. And so most 3D printers look like this when they're printing, and that works fine. This is a nice way to draw it out a little bit more as a diagram where all the layers come in, and then your hot end can sort of ooze out the stuff. And so you need to have some sort of an extruder that pushes the filament in, and then it melts and makes it go. Now, the pancake bot down here is delightful. If we ever get our hands on one, we should totally make use of it. The software is fantastic. You can see the quality of the astronaut in there is really good. I should just, here, let's find, we're gonna pancake bot, try and find images of the pancake bot, and this is totally using their image. But across here, Kickstarter, the Kickstarter has got to have some good photos of a nice set of the prints. And so in here, they've got videos. Look at all these pancakes that you can design and that you can print. Here, they're just going through and like drawing the Eiffel Tower with all of that craziness. And then it turns it into a pancake and it just spits it out from there. It's a really cool project. The earlier that it lays the goop down, the pancake batter, the darker it gets. And so you have all of this that contributes to the color of the thing. And so from here, the software is just incredible actually on these, which is usually the exact opposite of how a machine like this works. But it's lots of fun. This company unfortunately did their thing. Their Kickstarter, I think, was a big success. If I'm not mistaken, I didn't read this page that I have up. But then as a company, it ended up not panning out for them, which is very sad. But it looks like there was a lot pledged to bring this project to life. So some really cool things. People really like these. It's a standard, like, buy it at a big box store pancake griddle, and then a CNC machine wrapped around it, all done by belt drives. So it's really fun. Those are that's a cool machine. There are some machines that can do the same thing, but with ceramics. I think that would be a lot of fun to one day build one of these. It would be really cool. And then there's some of these that are multifunctional machines. Now, I've heard about these modular machines for a while, and I've heard that maybe there is one that's finally getting there. But the big thing that I've learned is that there's never been a dominant, this is the obvious one that everybody should buy. Things where you can swap out the end effector for a long time have been very appealing, but because machines often need slightly different calibrations, that usually doesn't work that well. Like a 3D printer needs to be built fairly solid because you're moving that print head around. You probably have a motor in the print head. So there's some weight there, and you need a little bit of stability because all of that is happening all in one shot. But the laser doesn't have nearly as much weight at the end effector, so it doesn't need to be quite as solid, and it would be better if it was more like smooth and graceful in how it goes. And then the CNC is going to need tons of rigidity because it's got a spinning end mill that's pushing into material, and so that you just have different needs with different machines. So building one with a frame that's good enough for all of them, but not so wildly expensive that no one wants to buy it, has been a tricky dynamic to hit. Allegedly, there's some that are good. This one without a second support to that vertical axis feels like an obviously this isn't going to work out for you design. But there's a few different ones that are cool. Oh, there's also like this thing, which I think is one of the circuit 3D printing machines. There's all sorts of cool end effectors out there. There's tons of neat ways to do this. But once you have some sort of an end effector, like the hot end here, basically you need these two sets of wires, the red and the white, to think about how you're going to control it. So at a low level, you need to have a low level is a computer sciencey term where it's the most basic ones and zeros to actually make something happen. And so low level control for something like a hot end is where you're going to be very precise about what it is you need to do. Like I want to apply power to the hot end in order for it to get warm. I want to apply power to the heater. And when I don't want it to get any warmer, I need to turn off power. That's low level control. We're basically powered on and it gets hot, remove power and it starts to cool down. Not that that has any consciousness of what temperature it is, not any of that, just that the basic controls of turn power on, it gets warmer, turn power off, it gets cooler. And then it gets a little bit better when you start to have like, okay, and then I also need to take this thermometer. And if you have feedback, now you've got a whole nother level of what's going on. So instead of just sort of guessing at the heat, you can measure how hot is it. And if it's cooler than I want it to be, turn the heater on. And if it's warmer than I want it to be, turn the heater off. And so you have this, it's slightly more advanced than low level control in lots of machines. This is probably something that we could stand to implement on our machine for the hot wire cutter, something with a thermometer attached directly to the wire that will be doing the cutting makes a lot of sense so that our wire doesn't get too hot, so that it stays at the temperature that we want it to be at, and so that we can make some sense of what's going on. And it just takes one of these little thermometers that we can literally like glue or tape or wrap the wire around so that it has good contact and that we can get an accurate temperature reading. But this ought to be pretty possible to do so that we can get a feedback loop inside of our thing. From there, you'll usually want to do some testing. So one of the things that we did last week for the people who were here is we did some low-level testing of the hot end where we applied power to the wire and we saw that it would get hot. And then we tried to measure how much current does it take. Does it take 3 amps of current? Does it take 1 amp of current? Is it a few milliamps for it to get warm? Not that you're going to need to micromanage that necessarily, but it's helpful to know in general so you know if your power supply is big enough. All those sorts of things are really important. It's also important so that you know exactly how to implement a kill switch to make it just turn off. And so you want to have some sort of a way that you can cut power to the end effector most of the time so that if something's going awry, you can turn off power. Like turn off power to the whole thing is great, but you might also want to be able to press a red button. And even if the whole machine needs to think for a second, you can stop the spinning end mill right now. Those sorts of pieces are important to think about when you're designing a machine. And it might make sense for us to have a switch on the side of our hot wire cutter that is like a ditch power to the hot wire now without waiting for the command to finish, without anything else, that it will just cut power and that's it. You don't have to wait for anything. And so while you're doing that, the automatic shutoff is better, I want to say. This is implemented in all current 3D printers. All of them have a cutoff, automatic heat cutoff. And if you don't, the 3D printer will often yell at you and say, like, I don't actually want to operate. It'll send error messages saying you don't have a thermometer on your hot end, so we're not going to print anything until you've replaced that. It's a very common problem because those wires are delicate, so they can die. A lot of times people who own 3D printers might buy spare thermometers, and that's totally fine. It's very helpful so that if you have a printer that happens to be prone to breaking those, like I think Crealities, those break actually kind of often. At least the one that I had, a student of mine had, he would replace those every couple of weeks. But knowing what that is important. But that thermometer can cut the power for you instead of needing a kill switch to do it. Then while you're doing low level testing, you'll want to think about how does the way that the machine work actually inform what you want your code to be. So if it uses different systems, you might want to think about how does the feedback work? When is it going to be high and low? How do I want to write my code, or how do I want to build the circuit so that all of this works? The low level control will probably start to tell you a little bit about how you're going to build the circuit. And that can be really helpful. It'll also probably help inform how your code's going to get written. Same thing for the power. When you're thinking about the power part of it, when you've done that low level testing, it'll help inform how you want to power things. Like we'll need to think about how we want to control our hot end. Maybe it'll be with a relay, or maybe it'll be with a MOSFET, so that we can control how much it's on or off. My gut says we'll probably want to use a MOSFET, sort of like one of these chips up here, so that we can drive the temperature to be exactly where we want. That's what they do on 3D printers, and it's probably going to be a good choice for us. And then there's some high level functions. So if you want to hit a perfect temperature, a perfect brightness, you can use pulse width modulation. And so that's how you get a fading LED like this. And we've played around with those before, where you analog write to a pin and you get a certain brightness. The same thing would be true for how you'd set your RPMs on a motor. So if you use pulse width modulation, you can set the speed of a motor, just like you can set the brightness of an LED. It works very much the same way. And then you can also, and so this has got simple G code that will come along with it. So you can play around with these G code commands to set spindle speeds and a few other things. But this is a really fun way to make, or a useful way to make all of that work. And with that, there's even more advanced things. So these are high level functions. Analog write is high level, not low level. Low level is like send a 1 to turn it on, send a 0 to turn it off. High level functions are where you are sort of describing what you want it to do. So I'm analog writing to an LED. I'm telling it I would like this brightness, please, or I'd like this speed on the motor, please. It's more of a description of what you're hoping for it to do in the function itself, which is really useful. These are high level functions instead of send a 1, send a 0. So that's a good trick. And then there's even higher level functions where you can do object-oriented code. And I want to see, and then there's something even more advanced called PID. And I'm going to Google that really fast for PID control Wikipedia so that we see it. This is a common way. This is proportional, integral, and derivative. If you took high school calculus and ever wondered, how the heck am I ever going to use this in life? This is it. Every time you've run a 3D print, you are using calculus directly, because there's proportional, then the integral, and then the derivative of your heating function, where you want something to get warm. Using the function, the integral, and the derivative, you can do a lot better than if you just say, if it's too cold, turn on the heater, and if it's too warm, turn off the heater. By doing calculus on how it's getting close to your target temperature, you can make interesting things happen where you like zero yourself into the perfect temperature that you want, and then it sits there as efficiently as possible. It looks really aggressive, but here's basically the system that you could do, where you can tune in some of the different settings and you can make it so that your values give you different results. So here's like, I have the heated bed at 0, and now I want it to be up to 1. I want it to be warm. You can make that happen, and a PID controller will sort of zero it in. Some people really like this curve for a heated bed, so that it warms up, and then it sort of tapers its way onto the final temperature that you want. Those are really cool, really, really nerdy ways to better understand what's happening here. But those are high level pieces. Object-oriented programming is also really great. So if you're trying to do all of these different pieces, if you're trying to get many repeated things, like if you have several actuators, or in the case of most CNC machines, you have 4 different stepper motors, you might do object-oriented programming, so you can treat each one of those the same, so that you have a nice, simpler interface inside the code. So those are all useful techniques to make that happen. The big things that we went through were thinking about how we get motion to happen, whether it's motors or the motion systems like belts or timing, or belts or lead screws that will make that happen. We talked a little bit about the end effectors and how there's a bunch of variety in those, and how you might have simple control or you might have PID control. We're going to go into those control systems a bit more next week. And we're going to talk about the feedback loops that are in there. So we're going to try and transition from sort of the machiney parts of it, the nuts and bolts pieces, and start to think more about like, how do you make the machine into something that's smart? So far, we haven't done a ton of that. We haven't wandered into it too much other than our little exploration of PID just now. But we'll start to think about that more next week as we explore all these things. Also, I'll talk less next week so that if you're here in the space on Monday, we'll be able to hopefully make some more progress on building the thing. Because as time comes and goes, we need to get ourselves closer and onto target. So that is the end of the slides for tonight. It brings us to the end of Unit 19 also. We are very close to the end of the new content in Foundations, and then we're cruising on to finish this project where we have this CNC machine and where we have then final projects that come along after. So that is that. Now we're on to the exciting bit. What have you guys been up to in the past week? What have you been doing? A little bit of show and tell. Let me stop sharing my screen.
Should I start talking?
Yeah, go for it. Go for it, James.
It's the three of us.
Yeah.
I was actually doing some weird kind of making that had nothing to do with MakeHaven. I mentioned in the fall that I work on a mooring boat sometimes.
Oh yeah.
To put in and remove those big moorings, the big anchors, and they wrapped up on Saturday building a new boat from scratch, because that's not really something that you can buy. Well, you could buy, but it would cost a fortune. So they bought like a pontoon boat and it was all kinds of crazy stuff, and basically like fabricated from scratch this boat that like I helped them put back together and launch, which was pretty cool and kind of terrifying, because you can also apparently just make a boat and register it. Like,
wow.
Will it work? Hopefully.
I mean, that's wild.
Yeah. Yeah, pretty cool. And then I just I got all my resin and rubber and all that stuff the other day, but I haven't had a chance to mess with it. So
for making holds?
Yeah, for making the holds. And I've like carved out like 15 different designs. I keep like messing with it when I'm like, not doing anything else. I'm like, okay, which of these am I going to make? But probably by the end of this week, I'll have that done. And then obviously I was in on Thursday playing around with the thing that we did, which I'm excited about. I assume on this upcoming Thursday, we'll be doing more of that.
Yep, and I will try tonight before I leave to set up some prints so that they should be ready for us when we come in.
Cool.
So that on Thursday, we'll be able to just sort of pick up from those pieces and make it happen.
Yeah, I can also get some of the stuff. I know you were mentioning that we have like a smallish budget. Like I can probably like get some of the stuff as well. As I mean, I don't have like a few $100s, but I
Yeah. Let me talk to Ashley, see what the real actual numbers are before we do any of that.
Okay.
But I'll see what's happening. It shouldn't be that big of a deal. And I think if we hit that 8mm size, it's going to be a lot cheaper for us.
Right. So his plans include the 10mm.
The 10mm linear bearings and rods.
Yeah.
And 8mm, and they're like out of stock. So if you can find well-priced 10mm linear bearings and rods, go for it. But I'm gonna try and find some things that aren't wicked expensive and then see if we can order them here.
Cool.
Yeah, because it would be if we can just use his model, that's the best.
Yeah,
just because it's easy. And so we'll see what's happening from there.
Okay, cool. That's all I have to share.
Yeah, awesome. And Norm, how about you? You're headed to Peru?
Yeah, and as I look into it, they had quite a lot of technology that they used in the old days before they got wiped out by the Spaniards. A lot of stone cutting stuff and water hydraulics projects that were, I guess, very sophisticated. So I might learn something about that. And they didn't use mortar in the stones. They all they knew how to cut them and place them so that they would just remain in place forever. That's why in many cases they still exist, even though the Spaniards crashed them down because they felt they were pagan, and built churches on top in some cases. Yeah, so I've been getting ready for that. I also, as always, have been making glacial progress on elements of the chest of drawers I want to make. So if you can enable screen sharing, I'll
Let me,
try to show
yeah,
a little bit of that.
it should be turned on now.
Okay. So the little particular thing I'm talking about, if you can see it, is these back plates that are used in drawers.
Oh, yeah.
I don't even know why they're so elaborate and finicky looking. In many cases, it's kind of like a little door knocker. I'm not going to have a dangling door knocker thing. It's just going to be a knob, but I thought I'd make a faceplate anyway. And I like the general outline of that thing, but not exactly how fussy it is. So Fusion 360 lets you kind of just play with shapes. And down here, I just came up with a shape that kind of was inspired by that kind of triangular version of this, and then rounded it. Cut it out with the scroll saw, created the blanks, which then seemed to need a little bit of ornamentation. So these are metal stamps that you can get that do a little bit of texturing. And when you pound with a hammer, you can make little indentations in the copper. And so I ended up, because there'll be two drawers, making two little back plates. The knob will go here, and this is just textured copper. I think I'll put polyurethane on it in the hope that it will then not tarnish for a while, because I like the color.
Yeah.
That's that particular increment towards the chest of drawers.
That's really cool. I really like those. And I thought they looked like leather at first, from the photo.
Yeah.
But it's really that's a neat way to do it. It feels so organic in the way that it's put together. It's really cool.
It's funny, the design, you could just freehand draw it, I guess. But there was something about Fusion 360, which is not organic, that nonetheless has functions that create kind of organic shapes that I wouldn't have thought to make myself. I would have been more likely just to draw a triangle around it, but you can just kind of play with the shape like dough with Fusion 360. And it came out, I think, looking more like an amoeba or something. So I had some fun with that.
Yeah, that's really cool. I am excited to see those with a knob. What kind of knob are you going to put with them? A copper?
No, I'm going to use the wood lathe to make exotic wood knobs that'll contrast with the other wood.
Oh, cool. Yeah, that'll be neat. I am fascinated to see how that works. And then a screw to hold through that opening.
Although, yes, I'm not sure that'll actually be a better, more powerful link than just good cement. Glue. Probably both.
Yep, that makes sense. Yeah, sometimes the screw to hold it as a clamp, and then the glue is perhaps more the strength, because the glue can stand a little bit of a squish and a pull, whereas a bolt has the tendency to snap, or a screw is sometimes brittle.
Right.
So the two together will help. Man, that's lots of fun. You've had a busy week too.
Well, it's mostly getting ready for the trip. A lot to do in that.
Yep, I bet. All right, well, I should let you get back to packing. I'm gonna do some 3D printing here. and get ourselves ready for the next round. On Thursday, we should have another round of come in and build. So James, if you're around for that, we should be able to start putting pieces together. I'll have the aluminum tracks. We'll have motors that we can start mounting. We should be able to make some progress on building a thing.
Cool. Yeah, I should be there around the same time as last Thursday, like just after 6 probably.
Cool. Sounds great.
Sweet. See you then.
All right. See you guys.